In an ideal world, the transition between state changes is clean and efficient, but in reality, there are many obstacles to that. Luckily, we have a concept known as Schmitt triggers, and in this video, we'll be discussing them, what problems they can solve, and how they can be implemented. So, what exactly is a Schmitt trigger? Well, it's a circuit that transforms a noisy or slowly changing signal into a clean digital output through hysteresis, or the use of two thresholds, an upper one and a lower one. Hysteresis is the property where output depends not only on the input, but on the system's history. And it goes beyond Schmitt triggers to other cases. But in terms of Schmitt triggers, this refers to the use of thresholds, where a rising signal to reach the upper threshold or the falling signal to reach the lower one to trigger a change in the state. The gap between the two is known as the hysteresis band. This band helps to minimize unintentional state changes due to switch bouncing, errant voltage, line noise, and unintentional analog shaping. This is also a bit of the aspect of analog to digital conversion, and it can be an aspect in timing and oscillation circuits as well. Now, you can sort of think of a Schmitt trigger as a type of comparator. A standard comparator switches its output voltage at a standard threshold. If it's one thing, it'll do, give you positive. If it's another, it'll give you negative. It's just making a basic comparison. Whereas a Schmitt trigger has two threshold voltages. This results in better noise immunity. It eliminates unintended output chatter or isolation, and it produces a clean digital output. You can sort of think as a Schmitt trigger as a comparator with positive feedback that introduces hysteresis. Now, what are the main ways that we can implement a Schmitt trigger? Well, we can do it with op amps. This is also called the analog method in some cases. We can take comparator ICs. We can use hex inverter ICs that have Schmitt triggers. That's key. Look for ones that say Schmitt triggers. This is probably the easiest way to do it. In fact, we can use bijunction transistors, Schmitt triggers. This is sometimes known as the classic method. We can do current mode Schmitt triggers. Sometimes people call this specialized analog. And we can use something like a microcontroller to do software based Schmitt triggers. Now, debouncing a switch, when we talked about switches before, we probably mentioned the problem with switch bouncing. Well, switch contacts don't always make clean transitions. This can result in unintended state changes or just not registering state changes at all. A Schmitt trigger requires certain thresholds to be met, introducing a debouncing circuit and ignoring really momentary contacts. The upper threshold is on, the lower threshold is off. Really, the simplest way to do this is simply to use an IC. Hex inverters with Schmitt triggers are probably the easiest and the simplest way to do this. All right, here's another quick example with switch to bouncing. There's some bounce put into here, right here with a PWL, and we're going to show how using resistor and capacitor with a Schmitt trigger can work here. And here you go. So the yellow here that you see, that's just to sort of represent switch bouncing. Keep in mind, this is in milliseconds. So yeah, your finger hits the switch, you get a little bounce here and there. Um, right here is our RC curve, the blue, if you remember that from previous videos. And then the, I guess, orange here is our proper switch debounced, as it were. Another use for a Schmitt trigger is to create an RC oscillator that just adds a resistor and a capacitor to create an oscillator that produces a square wave. That's the whole point of this. It's just to create a square wave. The specifics of the input or the output don't matter. It's just creating a square wave. But there are some useful applications for this. You can generate a clock pulse, a tone generator, an LED flasher, or even some form of time delay. As I said, the purpose is just creating a clean square wave, and whatever you put into the input doesn't really matter as long as you're getting an output of a clean square wave. The next use would be waveform shaping. You can convert a slow rising or distorted signal into very sharp transitions, such as a sine wave or a triangle wave into a square wave, or a noisy analog sensory output into a clean digital signal. The purpose behind this is digital electronics need a digital signal, unless they can perform analog to digital conversion. And in fact, this is actually a rudimentary form of analog to digital conversion. These sources might be magnetic pickups, hall sensors, audio tones, or function generators. This is where the number and the timing of the pulses are more important than the analog information in these waveforms. Next, we have noise immunity. Now, an inbound signal might already be digital and might be more or less a square wave, but somehow it's picked up some noise along the way. Well, this can cause an accidental misread of that signal. The noise itself could come from a number of sources: electromagnetic interference, capacitance, inductance. Just from the signal traveling through the wires, we talked about a lot of this when we talked about intro to wires, to say nothing of any noise that might be from processing by other components. This is kind of a similar problem to switch debouncing, except it doesn't have to do with actual button presses. Due to hysteresis, small variations won't reach that threshold, so they're just going to be completely ignored thanks to the Schmitt trigger. Another use is cleaning up slow inputs. Well, what do we mean by slow inputs? Digital signals want clean, sharp transitions with minimal rise and fall times. This is a problem similar to noise, but very specific to the rise and fall transitions of a signal. A noisy edge can trigger a threshold multiple times, pick up additional noise, cause jittery interrupts, and generate false signal counts. Many actions are dependent on rising and falling signal edges. The cleaner and the sharper, the better, and in some cases, absolutely necessary for steady operation. Two thresholds in hysteresis means no state change until a threshold is reached, a straight line transition. And then we have voltage threshold detection. This is something a little bit different. The point of this usage is the threshold levels themselves. Keep in mind, these are analog voltage values. You reach one voltage and it transmits the digital value. It reaches the other value and it transmits another digital value. This could be 0 or 1, off and on, whatever. That's not the important part. Hysteresis creates a dead zone between these two thresholds. For example, you might have a battery monitor that might determine if a battery is good enough. This could be one level, or it needs to be charged again. This could be another level. Another example might be a power circuit, needing to detect if something is over voltage, it's reached an upper threshold, or it's under voltage, a lower threshold, and the dead zone, meaning that the voltage is right where it needs to be and it triggers neither threshold. Now, here we have an example showing voltage threshold detection. We've got basically a voltage, and then we've got a reference voltage for that threshold. And noise has been introduced just to really push home the point of Schmitt trigger. So we've got a references voltage here, which I think goes up to like 2.610, and then it comes down to, I don't know, about 2.38 or so. So the voltages will start out, it starts out at 0, it goes up. Once it reaches 1 voltage, the state changes. So you're not seeing uh, crazy changes here. It's going to reach another threshold at top, and it changes, and it keeps changing. But it's a much smoother threshold change as opposed to what actually happens. State's only changing at certain points here. It's going up, it's going down, it's going up, it's going down. Um, we have a thing called pulse stretching. Well, There's times when a pulse is too short for a given purpose, and you need to stretch it out before it's sent to its intended destination. This may be a case where one pulse component outputs a particular pulse, but that's a little too short for the input of the next component in the circuit. You might have an emitted pulse that's, say, 100 nanoseconds, but you need an input pulse in the next component that's at least 1 microsecond in length. You can implement this a couple of different ways, like with an RC network with logic gates. You can use a variation on a 5x5 timer monostable mono vibrator, and in some cases, you can even use digital flip flops. All right, here we've got a little setup for basically we're going to convert a shorter pulse and we're going to stretch it out. Our example is a 1 microsecond pulse that we're looking to stretch out to 10 microseconds. Pretty simple as things go. We're going to plot our in and out as well as a signal going through our hub of sorts in one. All right, so let's take a look at the bottom as our in. So it's a 1 microsecond pulse. All right, now we'll see this is essentially the signal with our upper threshold, and then it reaches a certain lower threshold. And this is stretched out the signal here, and it's stretched out to, not sure if it's quite, and let's measure it out. Whoops. Oh no, it's actually saying, in this case, it's saying 8.7 microseconds, but I'm just going to call that close enough. Unless I'm measuring the wrong thing. No, 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 I think I am measuring the right thing. All right. On every circuit here, and this is effectively a Schmitt trigger made with a 555 timer. So we have a kind of, we basically have an analog signal. I made it kind of dirty here. We've got an upper and a lower threshold here. I can't remember which one's which. I think red should be upper and green should be lower, but it may have those reversed. But you'll notice it only goes to an upper when it hits a certain point in the analog signal, and then it only goes lower when it brings it back down. It's not going to respond whatsoever to negative voltage, purely positive. So all of this stuff from zero downward is completely ignored. Anything that goes above the upper threshold, that's going to be ignored as well. So yeah, in a way, this is converting analog to digital in a very basic way. Now, if you want to look at a somewhat more uniform version of this, uh, same idea as before. It's doing it again. It's only one sine wave, so it's converting a sine wave to a square wave. Now, this is a kind of another weird example I made a while ago, and I can't remember why I made it. I think it was just for different waveforms. But yeah, it officially does a Schmitt trigger in two different places, two different waves. Um, One's a loose sawtooth, basically, and it converts it into something that's sort of a square wave, basically. It's pretty uniform. Um, but yeah, it goes up when that goes down, and then when that goes up, that goes down. So it's got, upper and lower thresholds, and then basically the same thing there, except when that goes up, and we're seeing it in patterns of threes here, even though the third little sawtooth in each pattern is slightly higher than the first two. We're still getting the same result in the second Schmitt trigger here. Now, here's another little interesting thing uh, that we can look at for a Schmitt trigger. We can actually control the voltage here to see what happens. So we bring it up a certain point, we hit the upper threshold, it'll go on. You take it down, and it has to hit the lower threshold where it turns off, on, off, and it produces a square wave as a result. So if we were bouncing a button, say, okay, it's going to stay on, off, on, and the threshold, I believe it's at 1 volt and what, 1.5, something like that. It's only showing milliamps, so I'm looking at the wrong thing. Um, but yeah, no, just wiggle it around. Now it's not by me, it's by this person. Here's another neat example. Um, it's just a gentle analog wave going up and down, hitting the upper and lower thresholds here. And this is built around an op amp. Okay, here we're implementing a Schmitt trigger in Falstad with two bipolar junction transistors. I mean, it's pretty steady. We've got a slightly noisy analog being turned into basically a square wave. On the right here, we're plotting output versus input, and you'll see this characteristic S shape. And this tells you your lower and upper thresholds. So let's see what else we have. Another Schmitt trigger up here, this one with an op amp, but it's still the same idea. And then here we have a very basic one done with a 555 timer. We've got a noisy analog coming in, and we're getting a clean square wave. And we could probably plot both things together. Let's view in a new scope, viewing an existing scope. Let's plot them together or not. Let's see. All right, we have our XY plot here, same as we've seen before. So we can see our lower and our upper thresholds. Now, just to wrap things up here, a Schmitt trigger transforms a noisy or slowly changing signal into a clean digital one through hysteresis. Hysteresis takes in input and system history. We talked about how there's two thresholds, upper and lower. It won't change the state until it reaches either an upper or a lower, and it'll keep that state until it reaches the other threshold. We talked about signal switched bouncing, voltage threshold detection, pulse stretching, noise immunity, input cleanup, waveform shaping, and even RC oscillation. And we also talked about implementations with ICs, bipolar junction transistors, op amps, and there's even software based solutions out there as well. Well, until next time, have a good one.